So welcome again. Today we are going to discuss matrix rings and Boolean rings. So you are familiar with the ring of matrices. Let R be a ring and n a positive integer. Then the set of all matrices and cross-n matrices with entries from R under usual addition and multiplication of matrices. This set M and R becomes a ring. So it is necessary that these matrices have to be square. Otherwise, there will be a multiplication won't be a binary operation. And certain facts, again, you know, if R has identity 1, then the matrix ring M and R also has identity element, and that identity element is the identity matrix IN. That is, diagonal elements are 1 and rest entries are 0. If R is any non-trivial ring, even if commutative, then M and R is not commutative for n greater or equal to 2. For example, we take ring of integers and we take two matrices, A as this matrix and B as this matrix. Then AB is minus 2, 7, minus 4, minus 1, and BA is minus 9, 12, and minus 7, 6 as second row. And we see that AB is not equal to BA. So matrix ring is one of the examples of a non-commutative ring. There are other examples also. Yesterday we discussed CQ polynomial rings. So those are also non-commutative, and this is one more example of a non-commutative ring. Fact number 3, that if R is an integral domain, then the matrix ring is not so for n greater or equal to 2, because matrix ring has 0 divisors. For example, you take A equal to 1, 0, 0, 0 and B equal to 0, 0, 0, 1, then A is non-zero, B is non-zero, but AB is a 0 matrix. So M and R is not an integral domain. We have one more fact, diagonal matrix. Diagonal matrix is matrix A where all entries except diagonal entries are 0. So diagonal matrix, for example, A over Z, we take say 3 cross 3, say 2, 0, 0, 0, minus 1, 0, 0, 0, 3. So this is a diagonal matrix. And if all diagonal entries are same, then this is called a scalar matrix. So let A equal to Aij be a matrix and cross-n matrix. Then A is called a scalar matrix if Aii equal to A for some A in R for all I equal to 1 to n, and Aij equal to 0 for all I not equal to j. That is, diagonal entries are same and rest of the entries are 0, and the set of scalar matrices is a subring of M and R, and this is actually isomorphic to R. So this subring, the ring of scalar matrices, is isomorphic to R. So if we denote, for example, a ring of scalar matrices as S, then S is isomorphic to R. Another fact, the set of units, that is invertible elements of matrixing, is a group denoted by GLNR. This is the general linear group of degree n over R. But this situation arises in case R has identity. So if R has identity, then M and R has identity, and the set of units forms a group, and the group is called general linear group of degree n over R. So today we are also going to discuss certain notions which you are already aware about. You know about these things. Characteristic of a ring, but this is just recall it. The characteristic of a ring is the smallest positive integer n such that na equal to 0. So na, it is not n is not an element of it. So n is a positive integer and a is an element of a ring. Na will be a plus a plus a plus a n times. So if a plus a plus a n times equal to 0, we say that characteristic R is equal to n. And if no such n exists, we say characteristic R is 0. For example, characteristic Zn, for example, Z4, 0, 1, 2, 3. Characteristic of Z4 is 4. And one more characteristic of an integral domain is either a prime number or 0, P a prime number. So here P is a prime number, P a prime number. Next we discuss a Boolean ring. Boolean algebra you have studied in your course discrete mathematics, probably in your previous semester. And here we define a Boolean ring. A ring R is called a Boolean ring if a square equal to a for all a in R. So whenever a square equal to a, we say that a is idempotent. So if every element of a ring is idempotent, we say the ring is Boolean. So a square equal to a for all a in R means a is idempotent. That is, a is idempotent. So one fact about Boolean ring is characteristic of a Boolean ring R is 2. So we have to show that if A is a non-zero element of a Boolean ring R, then 2A equal to 0. We have to show it. So we start with A in R, and we have A plus A square equal to A plus A, because A plus A is an element of R and R is Boolean, so every element is idempotent, so A plus A is idempotent. But A plus A square is A plus A into A plus A, which is equal to A plus A. Here when we calculate it, it will be A square plus A square plus A square plus A square equal to A plus A, but A square is again A, using the same fact that A square equal to A. So A plus A plus A plus A equal to A plus A, and from this we get 2A equal to 0. So characteristic of a Boolean ring is 2. One more fact about Boolean ring is a Boolean ring is commutative. Let R be a Boolean ring and A be in R. We have to show that A be equal to BA. So this is a simple computation. So we have a plus b square equal to a plus b because r is Boolean. This means a plus b into a plus b equal to a plus b, and a square plus ab plus ba plus b square equal to a plus b. But a square is a, b square is b. So a plus ab plus ba plus b equal to a plus b. So from this we get ab plus ba equal to 0 because this a and a will go and b will also go. This means ab equal to minus ba. But we know that in the previous slide we have seen that in a Boolean ring x plus x equal to 0 for all x in R. So x is minus x. X plus x equal to 0 means x is minus x for all x in R. So minus ba will be equal to ba. So ab equal to ba. Therefore, ring is Boolean. Ring is commutative. So every Boolean ring is. Now we have some certain more facts about characteristic. Let R be a commutative ring such that characteristic R equal to P a prime number, then a plus b raised power p equal to a raised power p plus b raised power p for all a b in R. Number 2, prove that in a Boolean ring R every prime ideal is maximal, and prove that in a Boolean ring R every finitely generated ideal is principal. For first, we use the property, commutative property of ring. That is, whenever you have when you compute a plus b raised power p, you will get terms a raised power I, b, j, and here you can use this a and b commute. So this will be you will be using commutative property of the ring R. So this will be, for example, you want to take one b here, so you can write this as ai b bj minus 1, then b can come this side, so bai bj minus 1, like this. So as per requirement, you can twist this because you have ring is commutative, and you will get and furthermore you will get and whenever you get a term p, say, into some element of R, say p c, where c is in R, then this will be equal to 0. So you will be using two facts, characteristic R equal to p and commutative property, and the concept of binomial, and you will get that this a plus b raised power p equal to a raised power p plus b raised power p, but you have to verify it. So this is an exercise for you. So this is an exercise. Number 2 is, in a Boolean ring every prime ideal is maximal. Now for any ring a maximal ideal is prime. This is known to you, this you have discussed in your previous semester. But in certain situation a prime ideal is also maximal. One situation is if ring is Boolean, and some situation, more situations will come in unit 2, unit 3, so on, and we will discuss later on. But for the time being we discuss it for a Boolean ring. So I give us proof here. So we have to show that every prime ideal is maximal. Let xy in R. Now xy into x plus y is equal to x square y plus xy square, which is equal to x square is equal to x and y square equal to y. So this is xy plus xy. So x square equal to x square equal to x, and y square equal to y. So this is xy plus xy, and xy plus xy is 2xy, and 2xy equal to 0 because characteristic of a Boolean ring is 2. So xy into x plus y equal to 0. What does this mean? This means that either R has a 0 divisor or x plus y equal to 0. So either x plus y equal to 0 or R has a 0 divisor for every non-zero elements x, y in R. Because if x is non-zero, then y into x plus y equal to 0, then this is 0 divisor, y into x plus y is non-zero and x is non-zero, product is 0. That means x is a 0 divisor. Or if we take y here, x here, because this ring is commutative, so y into x into x plus y equal to 0, y is non-zero, x into x plus y is non-zero, means it's again a 0 divisor. So this thing means that either R has a 0 divisor or xy equal to 0, x plus y equal to 0. In the later case, that is if x plus y equal to 0, we get x equal to minus y. But minus y equal to y. Why? Because 2y equal to 0. 2y equal to 0 means y equal to minus y. So we get x equal to y. So R can have only one non-zero element because x equal to y. And if R has only one non-zero element, then R will be isomorphic to Z2. If ring has only one non-zero element, then this will be isomorphic to Z2, which is 0 and 1. Now we come to the prime ideal fact. Let P not equal to R be a prime ideal of R, then R mod P is also a Boolean ring with no zero divisors as P is prime, but R mod P is isomorphic to Z2 and Z2 is a field, so R mod P is a field, and if R mod P is a field means P is a maximal ideal. So here you have to use the fact which you have studied in your previous semesters, that M, if in a ring R, M, an ideal M is maximal if and only if R mod M is a field. And here you have got R mod P is a field, so P is maximal. And number 3, you will try yourself. This is an exercise for you. So number 3 is exercise. So 3 will be an exercise and you will try it. And when we have a virtual class, I will discuss it. With this, I thank you, and we'll meet in our next class. Thank you very much.